Hello everyone, thanks for joining us. We're going to get started here in a minute. I want to thank you all for joining us on the third of this semester's Ignite Speaker Series. If you've tuned in this semester, you know that we will have 3 mini-series as we go through the fall on different UN Sustainable Development Goals. And this talk will actually conclude our first theme on UN Sustainable Development Goal number 11, Sustainable Cities and Communities. And next week we will start UN Sustainable Development Goal number 3 on good health and well-being. So once again, thank you all for joining us. Thank you if you've joined us already this semester. If you haven't joined us before, my name's Matt Hawthorne. I'm an Ignite graduate fellow here at Clarkson University. I'm moderating today's talk, and we're going to be talking this week to Dr. Robert Thomas. And Dr. Thomas studied civil engineering at Clarkson for his BS in 2011, MS in 2013, and PhD in 2016. His experiences and passions have drawn him to focus his research on infrastructure materials, and he really misses an opportunity to express his love for concrete, which is what he'll do today. So we're excited to share that passion with him through this week's Ignite Speaker Series. With that, I'm going to pass it on to Dr. Thomas to begin.
Great, thank you so much for that introduction.
Of course, welcome.
I'm going to go ahead and share my screen here, hopefully, if we can get that going.
And as he does that, just a reminder that if you have questions at any point during the talk, please feel free to throw them in the chat, and we will ask them as we go through the Q&A portion at the end.
Okay, do we know if that's showing up?
It does look like it's showing up.
It does look like it's showing up. Okay, so as Matt just said, my name is Robert Thomas, and I love concrete. So the only person I know that loves concrete more than me is my wife, and the reason I say that is when I come home after a long day of talking about concrete and tell her about all the great things I learned, her eyes roll back in the back of her head in what I can only assume is sheer frustration that she didn't choose the same career path as me. So today, I'm going to be talking to you about sustainable infrastructure and materials. And as Matt just said, our Ignite Speaker Series is focused this year on the UN Sustainable Development Goals. And the UN Sustainable Development Goals are 17 goals for the world, right? Basically, they're really lofty, really aspirational goals that are focused on making the world better for everyone, focused on improving our environment, improving society, and improving our economy. So what does a concrete researcher have to tell you about the UN Sustainable Development Goals? Well, today I'm going to focus on how my research intersects with 3 of these goals, which are the ones shown on your screen right now. So industry, innovation, and infrastructure, that one's kind of obvious, right? Concrete is an infrastructure material. Sustainable cities and communities. How can we in the concrete research community contribute to sustainability in our communities and in our cities? And then responsible consumption and production. So how do we consume materials responsibly? How do we produce materials that are good for the environment, good for society, and good for the economy, while still achieving the goals that we need to achieve as infrastructure designers? So before we get into what we're doing in concrete research to address these goals, let's talk a little bit about sustainability. So you may know, many of you I think are Clarkson alumni, you may know about this special brand of sustainability that we teach. It has 3 facets, which are planet, people, and prosperity. A lot of times when we talk sustainability and sustainable solutions, we're focused on the environment. We're focused on green materials that have low carbon footprints or don't embody much energy. But there's really more to it than that. Our sustainable solutions also need to be sustainable for our people. Our society needs to benefit from all of the engineering solutions that we produce. And they also need to contribute to improvements in our economy. They need to be economically viable. Right? And we need to consider these 3 facets for now and all the way into the future. So let's now talk about sustainable infrastructure and what we're doing to address those 3 facets of sustainability within sustainable infrastructure. Now you may know that infrastructure kind of has 3 levels that we can look at it. That's the systems level, which is really our macro scale bird's eye view of infrastructure. These are our bridges, our dams, our buildings, right, our roadways. And we can zoom in a little bit and we can look at components, and we can talk about beams and columns and foundations and truss members and cables and all these things. And if we want to zoom in a little bit further, we're at the material scale. And this is really my domain. And this is where we're talking about not really columns, but the concrete that our columns are made out of. We're not talking about cables, but we're talking about the steel that those cables are made out of. And so what I hope to tell you about today is what we're doing in the infrastructure materials community to affect sustainability at the infrastructure level. So today's topic then is sustainable infrastructure materials. And I told you a moment ago that when we talk sustainability, we have three facets: people, planet, and prosperity. So let's start with environmental sustainability. How do we in the concrete research community address environmental sustainability of infrastructure? So this is one we've been working on for actually a long time. If you take concrete, right, it's composed of basically two things. It's a composite material, which means it's two things put together, all right? And that's a binder and an aggregate. So our aggregates are stone and sand, and they're held together by a binder, all right? And that binder is made of cement and water. The cement and water react together. They hydrate to form a hardened cement product, and that's what holds together our aggregates, which are normally gravel and sand. So when we talk about environmental sustainability in the concrete industry, we're really focused on cement. This is a Portland cement plant on your screen right here. And the way we make Portland cement is by taking limestone and some other materials, and we run them through a kiln. We essentially burn it at 1500 degrees Celsius. And what happens in that kiln is we create something called clinker. Now, this clinkering process uses a tremendous amount of energy, just an unbelievable amount of energy. But beyond that, we have another problem, and that's when we take our limestone and we burn it to make our clinker, which we then grind up to make cement. What happens is something called calcination. Okay, the calcination reaction is when we take limestone, which is calcium carbonate, and we burn it, and our byproducts of that reaction are calcium oxide. We call that lime, and that's useful for us in the cement industry because it's one of the reactants that creates hardened cement. But it also releases a tremendous amount of carbon dioxide. And if we consider the carbon dioxide released by calcination when we make Portland cement, and we consider the energy that we use to initiate that calcination reaction, it all comes to about 5% of anthropogenic carbon emissions. And cement plants are in fact responsible for about 5% of anthropogenic carbon emissions, which is a huge amount of carbon. And that tells us a couple things. First of all, that tells us that we have a lot of room for improvement in my industry to address environmental sustainability goals. But we also need to put it in context. We make about 10 billion tons of concrete every year on this planet. And it's the most consumed material in the world beyond water. Okay? And so if we're making that much material and we're only responsible for about 5% of carbon emissions, it tells you we're doing a pretty good job. And in fact, if we looked at numbers from 10 or 20 years ago, that number would be more like 7 or 8%. But we still have a lot of improvement, right? And so one of the interesting things is that in the concrete industry, we thought we had this environmental sustainability problem handled, okay? We thought we had it handled when we discovered a material called fly ash. Fly ash is a byproduct of coal combustion, and for years and years and years throughout the Industrial Revolution, we just put it in landfills. And then we realized, hey, this stuff is full of horrible things like chromium-6 and arsenic and mercury. But then somebody much smarter than me about 40, 50 years ago realized that we can replace about 50% of Portland cement in concrete with fly ash. Okay, and this is a great thing because first of all, you can see on your screen here a really zoomed in shot of fly ash. This is a scanning electron micrograph of fly ash. Got these round particles and they act like ball bearings in the concrete mixture and they make it really workable. They reduce the energy that we need to use to place the concrete and finish it. It also consolidates really well, so we get extremely good for performance compared to just Portland cement concrete. And as an added benefit, it's shrinking our carbon footprint by about 50%. We're diverting waste materials, important, dangerous, hazardous waste materials from landfills. We're making better concrete, and we're shrinking our carbon footprint. And that's a great thing. And so that's why I said we thought we had this problem handled. But what's going on with our energy systems today? We're closing coal plants left and right, and that's a good thing. Don't get me wrong about that. That's a great thing. We need to invest in clean power. The problem for my industry is that as we phase out coal power plants, we lose our supply of fly ash. And so 10 years ago, if you ordered concrete from the local ready-mix plant, it probably came with fly ash in it. You'd probably have to specify if you didn't want fly ash. But now, at least in our area, we can't get fly ash anymore. And the fly ash that we can get is low quality. So we need to come up with a different solution. This is echoed by Lafarge-Holcim, which is the largest manufacturer of cement and concrete products in the world. They released a bulletin called Tackling the Fly Ash Supply Issue in 2018. And that same year, the American Concrete Institute hosted a session at their annual convention about life after fly ash. And just this month, the Federal Highway Administration released a report on what does the changing face of electricity production mean for concrete, all tackling this issue of what do we do when we can't use fly ash. That was our easy solution for environmental sustainability. The answer, of course, is alternative cements. So what else can we use, right? What can we use besides Portland cement, which we know is responsible for a tremendous amount of carbon emissions and energy consumption? And what can we use besides fly ash, which was our solution but is no longer available? So the concrete research community right now is busy working on a number of solutions. They range from alkali-activated slag, which uses ground granulated blast furnace slag, a byproduct of steel production. Calcium sulfoaluminate cement, which uses a significant fraction of gypsum, which can be synthetic and which can reduce the amount of pyroprocessing or essentially the energy demand when we make the clinker, which is then ground into the cement. Magnesium cements, natural pozzolans. The Federal Highway Administration is investigating natural pozzolans, which are materials that are similar to fly ash. They behave the same. We can replace part of our Portland cement with them, but they occur naturally, and we don't have to rely on coal power plants for these materials. The big lesson we're learning, though, is that all of these materials work fine under a certain set of circumstances. And this is the big lesson that all of you students who are listening are going to learn, that all of you alumni who are listening have probably already learned, is that there is no magical solution to anything. What we always have are an arsenal of solutions, each one particularly poised to solve a certain problem. In my lab, we're focusing on calcium sulfoaluminate cement. Okay? Calcium sulfoaluminate cement is quite special because it reacts to form what you see here on your screen. This is our second scanning electron micrograph, and what you see is a needle-like structure. It's the hydration product of calcium sulfoaluminate cement, and it's called ettringite. Ettringite's really interesting because it, and by extension calcium sulfoaluminate, reacts very, very quickly. And so while we may wait for 4 to 6 hours for a Portland cement concrete to set, we may wait for 24 hours to remove our forms, we may wait for 28 days to put a load on that Portland cement concrete. With calcium sulfoaluminate, we can achieve setting behavior in 15 minutes, 1 hour, 2 hours. We can remove our forms in a couple hours. And we've got evidence that says we can make pavements, for example, that will be traffic ready in 4 hours with calcium sulfoaluminate cement. So calcium sulfoaluminate cement also has some environmental benefits, which I touched on a minute ago. But the point here is that we have all these things that each have their own environmental benefits, but our task as concrete researchers and in the infrastructure materials sector is to figure out where we can use those materials where they give us a truly sustainable solution. Now, the inevitable question is, what do we study? We study the fresh properties, we study the mechanical properties, and we study the durability. Now, to a layman, that means we're studying properties relevant to mixing, placing, and finishing the concrete. We're studying mechanical properties which are relevant to design so that we can validate existing design rules or modify them to be used with alternative cements. We study the properties relevant to service life. how these materials hold up under long periods of time in corrosive and weathering environments. And what we typically find, again, is that sometimes we do really well, sometimes we don't do so well. And my job and the specifier's job is to figure out where we can use these materials to maximum benefit. So we know that we can achieve environmental sustainability in the concrete industry. The question that comes next is, how can we achieve economic sustainability? This is a big question because every time I go to a Department of Transportation or to a precast plant or anyone like that, and I say, let's try something new, let's use an alternative cement here, the first question that comes up is, how much more is that going to cost me? And it's true, most of our alternative cements do cost more than Portland cement. That's why we've been using Portland cement for 150 years, right? Portland cement was patented in 1824 by a guy from Leeds, a bricklayer who made it in his oven at his house. And it's so cheap and it's so easy to make and it's so reliable that our industry has gotten a little bit lazy, and they're not willing to add to the cost, and they're not willing to fully analyze the economic picture. So when we need to use alternative cements, or when we're advocating for alternative cements, we need to understand the economic picture here. The economic picture has to do with how we calculate infrastructure costs, and there are really three infrastructure costs. Those are related to the design of the infrastructure, the engineering, the site work, right? The construction, actually putting it together, and then the long-term maintenance and operation costs. Now, I'm mostly interested in the construction costs, which basically break down to materials and labor, okay? So if we want to reduce the cost of infrastructure, we either need to reduce the cost of materials or we need to reduce the cost of labor. Now, our alternative cements, I just told you, cost a little bit more, so we're actually increasing the cost of our materials. But if we take a case like calcium sulfoaluminate cement, which I told you we can have a pavement, for example, that's traffic ready in 4 hours, if we consider the labor savings associated with that, you know, let's look at a typical highway construction project. We have traffic closures, right? We have flaggers. We have 4 or 5 people that are there just for safety. There's costs associated with just shutting down lanes, for example, if we're going to repair a pavement, okay? So if we can cut that labor down from a job that lasts 6 to 12 hours while we're waiting around for the Portland cement concrete to set and harden and become traffic ready, if we can cut that down by 1/3, we've just cut our labor by 1/3, or by 2/3 actually in that example. We go from 12 hours to 4 hours, we've got a 66% savings in labor. Even if our materials are 20 or 30% more expensive, our economic picture is much, much better, okay? Now, the other thing we need to consider here is the life cycle cost. So the life cycle cost, if you're not familiar with that term, is when we take our costs, our economic costs, our environmental costs, our societal costs, and we divide them by the service life. And instead of saying we spent $100 on a bridge today, we say we spent $1 a year for a bridge that lasts 100 years. So if we really want to improve our economic picture, what we need to do is minimize costs and maximize service life. So now our task in the concrete industry is to do research to figure out how we can develop materials that will maximize service life. So we understand how bridges fail, for example. We know that corrosion of embedded steel and reinforced concrete is a big problem. It's the #1 infrastructure problem in the country. And so how do we develop materials that can protect rebar from corrosion, okay? We have issues with aggregates sometimes, our sand and our gravel. Sometimes they create these deleterious reactions that tear the concrete apart from the inside out. How do we make sure that our alternative cements, which are environmentally sustainable, will not be susceptible to those reactions so that they can last 100 years or more? So these are the questions that we're trying to answer with concrete research right now. And the whole idea here is that we want to amortize our costs over a longer service life. And remember, this is not just the environmental cost. It's not the cost of the materials and the labor. It's the cost associated with the carbon emissions that we embody with the concrete we make, the energy that we embody with the concrete we make, the traffic closures that our society has to sit through. How do we make sure that we limit those? We stretch out the time in between them. We make them as short as possible, right? And this all points to extending the service life of our infrastructure. So that's economic sustainability. And we're just touching on this stuff, I know, and it's just a few examples of each thing here. But the next question we have to answer is, how do we address social sustainability with infrastructure materials? And I just sort of tangentially mentioned this a moment ago. Who likes sitting in traffic? I'm sure if this wasn't on Zoom, I'd see a bunch of hands raised, right? I love traffic. I love sitting in traffic, listening to a podcast, all of that. But most people don't. Most people aren't like me. And it turns out, the Federal Highway Administration tells us that traffic delays cost our economy about $200 billion a year, okay? And that's just the economic cost. Let's not forget our environmental cost, because all those vehicles are sitting there idling. Let's not forget the social cost of everyone stuck in their cars, getting angry at each other, throwing things out the window and everything, right? So how can we in the concrete community address this problem? If we go back to our calcium sulfoaluminate cements, one of the things I'm researching heavily right now, we know that our rapid repair mortars based on calcium sulfoaluminate can be traffic ready in 4 hours. So we can now take a bridge repair project, for example, if we're repairing a bridge deck that has some damage, instead of shutting it down for a day, we can shut it down overnight. We can go in, close it down at 10 p.m. We can spend about 4 hours excavating and prepping the site. We can spend another 4 hours placing and finishing and curing the concrete, and by 8 a.m. it's ready for traffic. This one hits close to home because almost 10 years ago now, Governor Cuomo released his Drivers First initiative, which said the New York DOT is no longer making decisions just based on cost. The primary directive for DOT projects now is to limit the impact on the traveling public. Why? Because the taxpayer is the one funding the project. Let's not inconvenience them more than we need to. Let's not have traffic backing up all the way from Albany to Saratoga, right? Let's not have people sitting in their cars idling, destroying the environment with their emissions. So this is social sustainability. That's the big thing with social sustainability is how do we make sure that our materials are contributing to a world where people are less inconvenienced by infrastructure construction. Now, we've talked about our economic, our environmental, and our social sustainability separately until this point, but at Clarkson we teach that they go hand in hand, that true sustainability happens when we consider all three of these. So let's talk about holistically sustainable infrastructure. Holistically sustainable infrastructure requires us to adopt something that we call sustainable engineering design. Okay? Sustainable engineering design is in contrast to what we call traditional engineering design. And there's a few principles that we in the materials community are practicing to reach a more sustainable, a more holistically sustainable infrastructure. The first principle is consider the life cycle. Right? We already talked about this one a little bit. But when we do sustainable design, we consider the life cycle, whereas in traditional design, we may just consider the upfront costs, okay? So we said we need to extend service life, and so we're working on materials that are immune to deleterious reactions or immune to corrosion, okay? This requires us to do something very challenging, which is to predict the long-term performance of a material. Now, we're innovating new materials every day. Calcium sulfoaluminate cement was invented in the 1960s at Berkeley, all right, but it didn't really see any practical use until about the 1990s, and it didn't really see any major research efforts until about the 2000s or the 2010s. Okay, and so we've been studying these materials for 10, 15 years. Somehow we need to predict how they're going to perform 100 years into the future. So this requires us to be very creative in coming up with accelerated aging procedures and test methods where we can understand what these materials are going to do, for example, under loads similar to natural hazard conditions, or under a corrosive environment, or in a weathering environment. It's very challenging, and we've come up with some really innovative things to do here that I won't go into detail with now, but I'd be happy to discuss later on. Second thing we need to do with sustainable engineering design is consider current and future needs, okay? And so we can ask some really practical questions here. We can say, Is this bridge deck going to hold the traffic load in 100 years? Is this bridge big enough for the traffic we expect in 100 years? But we also need to ask some kind of existential questions like, will we even drive cars in 100 years? Will this bridge be useful at all? Maybe we've moved on to something else. Maybe we've moved on to something beyond concrete. And so we need to take this into account when we're talking about our life cycle and when we're specifying a service life. Of course, we want to maximize service life. But if maximizing that service life means extending it past where it's actually useful, then that's not a sustainable solution. The third thing with sustainable engineering design is we need to consider the broader impacts of our solutions. Okay, we're not just focused on what's happening locally, but what's happening globally. So we need to assign value to diverting waste from landfills. We need to assign an economic value to that, a dollar amount, so that we can include it in our life cycle cost analysis. We need to assign costs to traffic delays and other social inconveniences so that we can consider those in our life cycle cost analysis. Otherwise, we're never going to be able to make a good economic argument for alternative cements. Even though we have a great environmental argument and a great social argument, economies rule, especially when you're dealing with bureaucracy. The fourth thing we need to do is consider systems and not components, okay? This means collaboration. This means materials engineers like me need to work with structural engineers and foundations engineers, geotechs, right? We need to work with policy people, and we need to understand how what we're doing, how the material that I make affects the overall design. Okay? We also need to consider targeted use. We have some really, really innovative solutions in the concrete research community that cost a lot of money, that are not so easy on the environment. And so we need to collaborate in the design process so that we can understand where we can make the case to use those materials, use them to their maximum benefit, and then use something else, use an alternative in another location. So my message to all the students and all the alumni out there is to take these four principles and let's drop the engineering nomenclature. Let's call it sustainable design. Take these four principles and apply them to everything you do. And you'll find that you'll make a better world, and you yourself will be addressing a lot of these sustainable development goals through your practice. Now, I just briefly touched on a few of the solutions that we're working on in the concrete research community in this talk. It was sort of a very high-level talk. What you see on your screen is a whole list of things we're working on right now. If you're interested in those, I'd really be happy to discuss them offline or in the questions and answer session. But for now, I really appreciate you all joining in today. I appreciate you listening in, and I'd be thrilled to take any questions or comments that you all have.
Awesome. Thank you very much. So at this time, if you want to start putting questions in the chat, if you have them, that would be great. In the meantime, I'll start with a couple of prepared questions, and then I'll move on to audience questions as we receive them. So you talked about a few different things when it comes to the materials that are available at the moment for alternatives. Are there any kind of low-hanging fruits when it comes to sustainable concrete as far as stuff that's available that we just don't utilize properly at the moment? Is it typically a policy restriction if this is the case? There's lots of policy restrictions. One of the policy restrictions we're used to is, let's go back to fly ash for example, right? Because we've been using fly ash for so long. One of the major hurdles with that is that we've been restricted by code to like 40% of the total cementitious material. So 60% Portland cement, 40% fly ash. We got research that says we can up that to 80% fly ash. If we use a process called alkali activation, we can up that to 100% fly ash. But the codes don't allow us to do that. The other thing that's restrictive is a lot of the fly ash that we are still producing, because of the coal supplies and all of that, it's very low quality fly ash. And we are not allowed to use that at all because there's some arbitrary standards that specify your fly ash must have this much calcium oxide, it must have this much silica. And if we miss that specification by a little bit, that material is completely excluded. That's not good for us because we can't use it in the concrete. It's not good for anybody because that goes in a retention pond. And if you just take a quick minute to Google fly ash retention pond failures, they are an environmental catastrophe.
The other low-hanging fruit right now is blast furnace slag. That comes out of the steel industry. It's basically the impurities that float to the top of the smelt. And we can use that in similar ways that we use fly ash. It's a really good material. Some states don't allow it, right? Some states don't allow certain aggregates. For example, recycled concrete aggregate. We can take old concrete, we can grind it up and crush it into the size of stone or into the size of sand, right? And we can use that as aggregate in new concrete, right? The aggregate has a much smaller environmental footprint than the cement, but if we don't have to quarry new aggregates every time, we're saving labor, we're saving money on aggregates, we're not depleting our natural resources as much. And we get a little bit of a quality drop, a little bit of a performance drop, but we can design for that. We're really smart about concrete these days. We can make it stronger with a little bit more cement. But most states are not allowing that right now.
So another thing that you discussed, and this could be tied to policy as well, the life cycle cost is a big piece of determining the sustainability of the material and whether it works for the application. A mentor that I have in sustainability, he often says that the only way to really implement sustainable design is to just have it be an all-around better solution and have it be so good that they can't deny that they need to replace whatever they're using now with this new idea. And you talked about that a little bit with the faster cure times on some of these alternatives. Can you discuss how effective talking about the economic viability or maybe the faster cure times is in persuading DOT or other companies to adopt these alternative materials?
Yeah, that's a really interesting question because we can go in and we can make a great economic case. For example, maintenance is a great example of this with road maintenance particularly, right? Our bridge decks are in terrible shape. Our infrastructure is in awful shape. If you believe what the ASCE infrastructure report puts out there, which is a little bit doom and gloom, our bridges are not all falling down. Let's start there. But if you believe that, you'll believe that they are, right? And one of the problems is deferred maintenance because maintenance is expensive. If we have potholes, we got to go in and cut around them. We got to excavate down. We got to be careful of the rebar. We got to put new concrete in, finish it, and all of this takes a lot of time and money. Right? The issue, though, is that what we're doing now is we're chasing the worst problems. And so there's this old adage that says if you spend $1 on preventative maintenance, you're going to save about $20 on replacement down the line. That's specific to highways, basically. But the point stands for all infrastructure. So if you've got a bunch of bridges that are, let's say, almost falling down, and you got a little bit of money to spend, you're certainly going to spend it on those, right? You're not going to be able to, you just don't have the budget to go through and do preventative maintenance on your structures that are not falling down. So the problem right now is, yeah, we can make a great economic case for things like that, for using rapid repair materials, for making structures more repairable and things like that, but we're chasing ourselves around just making sure that the house doesn't fall down right now, and we don't have time to clean the kitchen floor.
Gotcha. So if that's the case, what does long-term sustainable concrete actually look like to you? What's the ultimate goal as an industry that you're trying to get to? Does it relate to emissions? Does it relate to material consumption, recyclability? What are the metrics that you guys are really looking at?
So the primary metric right now is environmental, and it's all about what we call the embodied carbon or the embodied energy. That's if you take a concrete structure, for example, how much carbon was emitted in the whole process of doing that, from mining the raw materials, making the cement, pouring it, curing it, all of that stuff, right? And the same with energy. How much energy did you use and what sources did that come from? So, one of the big things years ago was that one of the cheapest ways for cement plants to get that kiln up to 1500 degrees C was to basically just burn coal or other fossil fuels. Just burn them directly. We've kind of stopped that because we can produce electrical energy a lot more efficiently offline, right? But we're still dealing with that embodied energy. How can we reduce it, okay? And so a picture of true sustainability in the concrete industry would be all of our specifiers understanding that we have a suite of materials, an arsenal of materials, and understanding how much CO2 per kilogram of this type of cement, that type of cement, and a third type of cement? How much embodied energy? And taking those costs into account and adopting some sort of life cycle cost analysis, life cycle environmental analysis in our bidding process for infrastructure. So when a contractor makes a bid on a bridge, for example, a design build firm, they should have to submit a life cycle cost analysis, a life cycle environmental analysis, and say, we're going to use these materials. This is how much carbon this is going to embody. This is how much energy it's going to embody. And now you're not just competing on cost, you're competing on sustainability. And we need to encourage that, and we need to develop a framework by which we can make decisions, make fair and equitable decisions at the DOT level, at the owner level, so that these companies can feel comfortable and confident in bidding that way. So they can feel comfortable submitting a bid that's 10% higher in cost, but 20% lower in carbon emissions.
And do you think that there is also a relation in, you talk a lot about finding the right material. Do you think that there's some extent of engineers pick the concrete that they're most used to? Like, do you think that there's a lot of projects out there that could use a different alternative that might be less strong but is definitely more sustainable and will last just as long for that type of application?
Yeah, there's a whole lot of that going on. There's a whole lot of people using what they know. Okay. People using what's available easily, right? You pick up the phone, you make a phone call to the ready mix plant, and they have whatever they have. They have a mix that's already designed, it's already DOT approved, right? If you're going to adopt an alternative cement or a recycled aggregate or anything like that, you've got to go through an approval process. You got to make sure the DOT says, okay, you got to do all this testing, the same testing we're doing in the lab, the mechanical properties, the fresh properties, the durability properties. You have to prove that that material is going to meet the specification. The other thing is that a lot of designers are not aware of alternative cements, and that's actually something that we're working on in the American Concrete Institute with ACI Committee 242 on alternative cements. We're going through right now and writing reports, useful reports for specifiers that say, here's calcium sulfoaluminate cement, for example. This is what it's good at. This is its environmental picture. These are some situations where we've used it and what experience we have. And we're going through and writing these technical reports on all the different alternative cements that we're researching right now so that we can release them kind of as a volume for specifiers to say, okay, let me look here. I'm looking for something that's going to give me early traffic ready time, or I'm looking for something here that's going to give me the absolute minimum carbon footprint and I don't really care about anything else. We don't have that right now. People like me have that knowledge. And one of the things that my industry is not great at is transferring that knowledge into practice. You can talk to different types of engineers. You can go talk to computer and electrical engineers, and their innovations are in practice in 6 months, right? If you talk to mechanical engineers, their innovations are in practice in a couple of years. You talk to civil engineers, our innovations are not in practice for 25 to 50 years. And the reason is the useful life of what we're making. You can make a computer and it'll last a few years and your client's happy. But if I make a bridge with a new material and it only lasts 5 years, I got to move to a different country.
So that actually leads into the next question that I had, which was, it sounds like a lot of the innovation is happening in academia and in university institutions, whereas some of those other industries, the companies themselves are doing a lot of the R&D. So do you think that has an impact on the adoption rate on some of these new alternatives?
Yeah, it definitely does. And we're seeing some companies pop up, a lot of startup companies, but we're also seeing Lafarge Holcim, what I referenced as the biggest manufacturer of cement and concrete products in the world. Second biggest is Heidelberg Cement, which I believe is based in Germany. These startups, but these two big ones especially, are now starting to open their eyes a little bit and say, hey, there's interest in this, right? And so with calcium sulfoaluminate cement, Heidelberg is making that now. It used to be a fringe product that was made in Juarez, Mexico by a company that was based in Anaheim, California, and it was produced at such a low volume that it was incredibly expensive. Now Heidelberg Cement is looking at making that, and they're going to be able to do it because of economies of scale. They're going to be able to do it much more economically. And because it's coming from a major manufacturer, it's going to be more widely accepted. And they're going to push that on the market and try to get people to use it. So that is going to be a huge positive step in the direction of sustainable materials.
And do you think that that's a lot because of them wanting to move in a sustainable direction, or do you think that that has largely to do with the fly ash shortage?
I think it has to do with both, but a third thing is that projects are now going for these certifications, LEED certification, BREEAM certification, all these other things, right? And it's not hard to conceive of a time not too far from now where it's going to be a requirement to meet a certain embodied carbon goal for a structure or a certain embodied energy goal. And I think that these companies are looking ahead to that time and saying, we know it's coming. We know that eventually every product we sell is going to be analyzed for its embodied carbon, its embodied energy, et cetera, its use of renewable resources. So we better get on top of that, and we better make sure that our customers have a solution that they can justify within whatever framework is developed over the next decade or so.
And along those lines, it sounds like, these third-party certifications like LEED are really important. Do you think that they have enough importance to kind of carry the industry into the future that you're looking at? Or do you think it really is going to come down to policy at the end of the day? So
with infrastructure, no. LEED certification, it's great for buildings. It's awesome for buildings. I love it. We have a few LEED certified buildings here on campus. But if you go back to when Obama was president, Obama released an executive order that said you can go for gold. That's it. You can't go for platinum or whatever because it's too expensive, right? And in infrastructure is already expensive, right? The Tappan Zee Bridge was like $2 billion or something like that. The Governor Mario Cuomo, whatever bridge. It's too expensive to add the costs that would be required to get LEED certification. It's going to be a policy thing because society is going to have to rise up and say no more, right? We know it's expensive, but we're demanding a better environmental footprint, better social sustainability. And so it's going to have to be policy driven because you don't see any LEED certified bridges, right?
Yeah. So in agriculture, there's some estimations about basically how many years we have left of good yielding crops, and because the soil level is decreasing. Is there any estimates on the levels of resource we have left for whether it be the aggregates or cement materials in general, before basically, just in case policy doesn't catch up? What's the worst case scenario of what we're looking at for that transition?
So I don't actually, I gotta be honest, I don't have a great picture of that, but I will tell you that in some places it's already hard to get good cement. I did my postdoc in Utah, and the cement we got in Utah, while it met the specification perfectly fine, it was not nearly as good. It didn't produce the quality concrete that we produce out here. There's areas where it's hard to get good quality aggregates. I'm thinking of big chunks of the Midwest. Like I have a colleague in Nebraska, and every aggregate in the state of Nebraska has been disqualified by the Nebraska DOT because it contributes to this deleterious reaction we call ASR, and what that is not important. But they need a solution now. They need a solution for aggregate right now. Some places need a solution for cement right now. So it's going to be very localized because cement plants are localized. Aggregate quarries are localized. So around here, plenty of limestone. State of New York, the entire Northeast, will be making Portland cement until you and I are long dead, right? But in other areas, those materials have to be trucked in. In some areas, energy is too expensive, and so that's going to accelerate the transition to materials with lower embodied energy. Up here, it's all hydropower, and we have some of the cheapest energy in the country. So it's going to be regional, and I don't have a good picture of it, but it's already happening.
And you think that, so from that perspective, the transportation costs to get traditional aggregate or cements to those areas that already have their disqualified materials, that's going to start increasing significantly, and will push that transition.
Yeah. As soon as they start doing economic analyses to say, okay, in Nebraska we've got to truck aggregate in from, Ohio or something like that, Hopefully they don't do that. And hopefully they're considering beyond just the economic cost. Hopefully they're considering the environmental cost of trucking and the social cost of trucking, right? And that's why we need to do these more holistic analyses here so that those tipping points happen sooner rather than later. And so that we're not just worried about the bottom dollar, we're worried about what we're doing to our planet and what we're doing to our people.
Absolutely. Well, that was great. I don't have any other questions. Are there any questions from the chat? Doesn't look like it at the moment. Well, I'm going to cut it a little short then. I think we went through a ton of really high-level things. If no one else in the audience has any questions, I'll be respectful of everyone's time. I want to thank everyone for joining us. I do want to recognize that there was an issue with the Zoom link or the registration link. I did get that through chat. We will be sending out an announcement to everyone. It will probably go out to alumni as well, recognizing this with the YouTube link so that everyone who had registered can get it. So if you showed up late and you missed part of the talk and you want to go back and see it, or you know someone who wasn't able to get in, please let them know that the YouTube link will be in. We'll be coordinating with alumni relations to get that info out to everyone as soon as possible. I want to thank all of you who reached out to us at Ignite to let us know that we had issues. It made it a lot easier to get on top of this now, and hopefully some of you were able to at least catch half or most of the talk. So once again, Dr. Thomas, thank you very much for joining us today. This was an awesome conversation.
Thank you so much for having me. And if there's anybody out there that wants to ask like a detailed question or anything, please shoot me an email or give me a call. Happy to talk concrete anytime.
Awesome. Thank you, everyone.